This is content of part 6. If you're interested only in specific part of this video, just jump to its start time. Next, I will discuss properties of measured magnetic field, which is created by the accumulated spin-polarized electrons, or offset magnetic field in short. The spin accumulation means that there is a group of conduction electrons whose spin are aligned in one direction. The spin accumulation is created by electrical current due to, for example, the spin Hall effect. A small magnetic field created by the magnetic moment of each electron is summing up, and the total magnetic field becomes substantial and measurable. The offset magnetic field is perpendicular to the magnetization, which is shown as blue ball, and therefore it slightly tilts the magnetization out of its equilibrium perpendicular direction. It's called the offset magnetic field because it corresponds to an offset out of the center during a measurement of anisotropy field. When in plane magnetic field is scanned from minus to plus value, the measured Hall angle dependence is not centered but is slightly shifted from the center. It can only be due to an existence of additional magnetic field, which is called offset field. Offset field has two in-plane components, along current and perpendicular to current. Some animation refers to offset field as SCI, meaning current induced, or H-sword, meaning the magnetic field of the spin orbit torque. You may recall that after fitting the measurement data, we obtained two data sets, one for anisotropy field and one for offset field, which are recorded into these four files, corresponding to two directions of the scan. Along the current 0, 0 and perpendicular to current 9, 0. This data is shown in analyzing program in these four graphs. The x-axis is perpendicular external magnetic field. The light of different color corresponds to a measurement at different current. These two graphs are anisotropy field, which details I have discussed in the previous video. These two graphs show offset field, which I will discuss now. Please note that measurement of anisotropy field is nearly identical for two scan directions. It is because anisotropy field is a scalar. In contrast, offset field are very different for two scan directions because offset field is a vector. About the value of the offset magnetic field, it's about 75 Gauss. You can see 75 Gauss for a single layer nanomagnet with small coefficient of spin-orbit interaction. So nanomagnet only has one ferromagnetic layer like this. It is about 200 Gauss for multilayer nanomagnet with large coefficient of spin-orbit interaction, which looks like this. Many layers. Another fact is that the offset field has both the current-dependent and current-independent components. As you can see, value of the offset field is very different for different current, which correspond to line of different color. But offset field does not vanish at zero current, so it's about blue line. In absence of any current, still there is some offset field. We can also see it for single layer film. So this is still offset field even at zero current. Even so, offset field is rather small, of about 70 to 200 Gauss. An external magnetic field of the same strength cannot possibly reverse the magnetization of nanomagnet. Offset field can efficiently reverse the magnetization of nanomagnet because of its dependency on current and the effective parametric mechanism of magnetization reversal. I will talk about the currency dependency of offset field and the magnetization reversal by this field in another video of this video set. Now I would like to discuss the current independent component of offset field. Let us analyze offset magnetic field in absence of any current. Since the whole angle cannot be measured without any current, let's analyze offset field at negligibly small current. From these graphs, let us take only the data correspond to the smallest current. See here the current in milliamps per square micrometer, so let's take 10 milliamps, which is very small. So just copy, go to the origin, copy there, so that is the X, and the third data, like this. And let's do the same for this and this data. So that is the offset component along current, offset component which is perpendicular to the current, and this, and this is this perpendicular component versus along current component. This one. All measured at very small currents, so practically in absence of any current. Several properties of the offset field can be noted from these graphs. The first property is symmetry, meaning that it looks like that polarity of component along current changes its polarity when external magnetic field is reversed. In contrast, the polarity of component perpendicular to the current does not change. I would like to emphasize that such a symmetry only looks like but does not actually exist. It is an important fact when the data of second harmonic measurement method will be discussed in one of the following videos. The incorrect interpretation of this symmetry leads to incorrect introduction of the not-existent field-like torque. The second property is that there is a large step of offset field at the zero external magnetic field. You can see a step here and a potential step here. It means the direction and the magnitude of the offset field depend significantly on the magnetization direction. So we come to these important properties. So offset field depend not only on external magnetic field but on the magnetization. The coercive field of this nanomagnet is not so large, and magnetization reverses its direction at magnetic field equal to 0. The parameters which are proportional to external magnetic field should be changed continuously through the zero external magnetic field. A step-like change is only possible when a parameter depends on the magnetization. The third property is that both components of offset field are related. Means that the component of offset field along current and perpendicular to current do not look like two independent properties, as it is often assumed due to the different symmetry. It is more clear when we look at one component plotted against another component of offset field. External magnetic field is parameter which is changing from a negative value here to a positive value. It looks like offset field changing its direction under increasing of external magnetic field. Here the magnetization is reversed, causing reverse of offset field. Next, offset field is changing its direction again. And the fourth property is that offset field is different for single and multilayer nanomagnet. This data is for single layer nanomagnet with a small coefficient of spin-orbit interaction. It looks more like this, but the offset field for multilayer nanomagnet like this is very different. We just can take a look, just copy data here and read all. You see its dependency is very different, and if we plot two components against each other, it's also very different. So if it's data for single layer nanomagnet, for multilayer nanomagnet data looks like very different. You can notice it's 80 to 100, so offset field change of offset field is more significant, and also it's look like change is only of the component along the current, and perpendicular to the current components stay almost constant. If you are interested to see the content and other parts of this video, you can find the links below this video.